So much of the sulfur dioxide will actually react with the water vapor droplets, and before they precipitate as sulfurous acid, it actually acts as a better reflector from the solar radiation back to space than would only the water vapor droplets or clouds. One other category of aerosols, referred to as black carbon, come from soot that happens from fires or from combustion processes. This type of aerosols, the black carbons, act more like an absorber of long-wave radiation from Earth than a reflector of the solar radiation. And also, apart from their effect to warm the atmosphere, once they settle on the surface, so once they fall, it is very likely that they will reduce the surface albedo where they fall because of their color and their properties. Again, namely they are black carbon, so they will have properties that will reduce the surface albedo. But despite the effect of the black carbon, most of the other aerosols tend to actually cool the atmosphere, like the sulfur dioxide example that I gave you. And some of the human-caused cooling, or I should say, and although some of the human-caused cooling does counteract some of the input of the greenhouse gases that are warming the atmosphere, we are still uncertain to know about the quantity of the cooling that we're doing versus the warming that we are doing from the human-generated activities, or from the human-generated gases and aerosols based on our activities. So overall, we have uncertainty and we have an inability to act upon our actions to the degree that we would like to, but at least we're getting there, hopefully. So also, it's important to clarify that the residence time of the greenhouse gases in the atmosphere is going to be in the order of years to decades, but the residence time of aerosols in the atmosphere is typically only in the order of days or weeks. So although the first one has an effect to warm the atmosphere, they will remain in the atmosphere for a lot longer than the second one, which has an effect to cool the atmosphere. And obviously, they will also change and be concentrated in the areas where they are produced. And again, I'm referring to the aerosols here. So again, to kind of condense that, the greenhouse gases remain in the atmosphere for a lot longer, and because of their nature of being gases, they actually intermix quite well and have an effect globally. But the aerosols, which are heavier, tend to only be concentrated in areas where they are produced, and they only stay in the atmosphere for a few days or a few weeks at most. Okay, so now we're going to go ahead and cover the climate feedback mechanisms. So because climate is so complex and so dynamic, when a component of the climatic system is altered, there may be many possible outcomes to this. So it is these outcomes which we name climatic feedback mechanisms. For example, a climatic feedback mechanism is associated with greenhouse gases that increase the surface temperature, and this in turn increases the evaporation rates. The evaporation rates in turn will increase the amount of water vapor in the atmosphere, which in turn will continue to increase the surface temperature because water vapor is a great absorber of the long-wave radiation from Earth. Another example is based on the amount of temperature rise that there will be in the high latitudes versus the lower latitudes. So, because much of the higher latitudes are covered by sea ice and snow, as the surface temperatures increase, these will begin to melt, the snow and the ice. And so, no longer having the greater albedo effect that they typically have, the land and the open waters that are now exposed will start absorbing much more of the solar radiation than the one that was being reflected by the ice and the snow beforehand. So the absorption of greater solar radiation is much greater at the higher latitudes due to this change in the surface cover. So that is partly also why we are seeing the greater temperature changes in the higher latitudes than we do see in the lower ones. So these two examples that I just gave you are both types of positive feedback mechanisms. Because they're positive feedback because in both cases the temperature increase is magnified as the cycle continues. And as this continues, there is a reinforcement for the temperature to continue to increase. So it's an ongoing loop that is feeding on itself. On the other hand, a negative feedback mechanism is produced when the results are just the opposite of the initial change, and they tend to offset that change. So one example of this is actually a similar example to the first one that I gave you. So in this case, however, for it to become a negative feedback mechanism, the cloud cover that formed after the increase in evaporation rates due to the increase in temperature actually causes a lot of reflectance from the shortwave radiation from the sun. So cloud cover actually produces two opposite effects. One is going to be a negative feedback where the cloud cover is reflecting some of that solar shortwave radiation back to space, and hence it's cooling the atmosphere, hence offsetting the initial temperature rise. And then the other effect that the cloud cover has is a positive feedback loop where the cloud cover is absorbing the Earth's long-wave radiation, and hence it's warming the atmosphere in that way. So in this case of cloud cover, you might wonder which of these effects is greater than the other. So after many observations, scientists have seen that the warming caused by the buildup of greenhouse gases is slightly offset by the increase in cloud cover. So overall, the cloud effect is the effect of the clouds is to slightly cool the planet. So just driven by, again, water vapor. So these type of cycles that I have mentioned here and these mechanisms are being modeled every day now to see what kind of effects are really taking place from our input as humans, and also to see what the extent is as it continues to drive climatic changes. So this modeling is being done through GCMs, or global circulation models. So these models attempt to simulate the changes based on fundamentals of physics and of chemistry, and they take into account many different variables like the temperatures, the precipitation, the snow cover, the wind currents, the cloud cover, the sea ice, and the ocean currents at the locations. And again, this is harder to do on a geographically constrained area than on a global perspective. So, however, even though these models are attempting to do this work, which is not easy, models are imperfect and they cannot capture the full complexity of the Earth's processes. They can make assumptions and they can simplify these processes a bit, but yeah, they're not perfect. So these models don't only have to take into account, again, these climatic and geologic processes, but they also have to take into account changes in population, changes in economic growth that they predict, changes in the fossil fuel consumption and other types of energy use, any technological developments that there may be, any improvements in the energy efficiency of things. And lastly, they also have to take into account the constant changing political atmosphere. So, as you can see, again, these models are not easy to build. This is a very hard task. And as they're doing this, there may be many hurdles that they have to jump through, and they have a lot of uncertainty and assumptions to make as well. But our ability to model things is getting better and better with the developing world. So my sister actually, who is an environmental economist, works in trying to do just this, to do these economic models for climatic change. So she works for the New Climate Economy, which is a nonprofit organization in DC. And because of this work she does, that is one of the many reasons that I admire her so much. Okay, so now we're going to go ahead and cover some of the consequences of global warming. So any consequences from the increasing greenhouse gases is really speculative. Again, this is speculative due to the complexity of the system itself. It is not possible to really pinpoint any of the said changes, but there are plausible scenarios for a large scale of space and of time. So here we'll go through a few of these proposed consequences that, again, are not for sure going to happen, but they are made through speculations based on our observations and our studies of the system. So as noted before, the temperatures will increase, but this increase will not be the same everywhere. It will probably be the smallest in the tropics, and it will be the greatest towards the poles. The table that you have right here on the slide shows a few possible effects of global warming based on the IPCC's projections for the late 20th century or 21st century, and these are ranked in the order of certainty. So these probabilities that they have listed here are based on the quality, on the volume, on the consistency that they have based on the evidence that has been gathered and the extent of agreement among the scientific community. So I won't go through each of these possible consequences, but I highly encourage you to check them out. They're also on your book, table 20.1. So go ahead and pause the video and go ahead and read those. So from the table above in the last slide, you saw that one of the most significant impacts of this human-induced global warming is the rise in sea level. So this rise in sea level will cause coastal cities, it will cause wetlands, it will cause the low-lying islands to actually be threatened with greater flooding, with greater shoreline erosion, and also with saltwater intrusion into the coastal rivers or into the aquifers. So this sea level rise occurs with temperature increase by two main ways. So the first one, and perhaps the more obvious one, is by the melting of the glaciers. So as we saw in chapter 15, most glaciers are actually retreating around the globe. There are a few exceptions to these, but we have seen many alpine glaciers retreat, some of them disappearing altogether. So a study on the melting of Antarctica and Greenland glaciers alone showed that as an average of 20 years, they lost enough volume to have contributed to the sea level rise by 1.5 millimeters per year. So throughout the 20 years, it was about 1.2 inches or so. So again, this was just from the Antarctica and the Greenland glaciers. And the melting that was observed from other alpine glaciers was of the corresponding 1 inch of sea level rise in those 20 years. So clearly this is one of the main factors that is contributing to the sea level rise. The second way is through thermal expansion. So higher air temperatures warm the adjacent upper layers of the ocean, and as we've seen throughout the class, with warming of a material by the intermolecular motion, there is an increase in the volume, which is otherwise termed as an expansion. So thermal expansion is the second way in which we're seeing sea level rise as well.